Okay, so in this video, let's take a look at another example for solving a system of linear equations, applying this method of row reduction in order to express the augmented matrix in reduced row echelon form. So now we've got a system of two linear equations in three variables, x1, x2, and x3. So the corresponding augmented matrix has two rows corresponding to each of those equations with four columns. The first three corresponding to the coefficients of x1, x2, and x3, respectively, and the last column corresponds to the constants on the right side of the equation. So the process says, well, let's identify the pivot column first of all. And since our first leftmost column has non-zero entries, that's our pivot column. And the top entry in this column already is non-zero. So we've got our first pivot, which is the 1 in the top row. And what we can do next is we want to make sure all of the entries below this pivot are 0. So there's just one entry, which is the one down here. So we want to eliminate that by using a replacement operation. So I'm going to replace row 2 with -1 times row 1 plus row 2. So I get -1 plus 1, 0. -2 plus 3, 1. -1 minus 2 gives me a -3. And then -1 times this gives me 2 plus 1. That's where the 3 comes from. And now I've got my second row over here. And in this second row, the pivot would be this entry of a 1 right here. So that's great. So now I've got my matrix in row echelon form. I actually have both of my pivots are 1. And so the last thing that we want to do is make sure that we get zeros not just below each pivot, but also above each pivot. So there's only one entry that I need to worry about, and that is this 2 that's above my second pivot. So now I'm going to do replacement on the top row. So in particular, I'm going to take -2 times this bottom row and add it to the top row. And so that would eliminate this entry over here. I get a -2 times -3, add 1 to it. That's where the 7 comes from. And then I get -2 times 3, which is -6, -2, and that's where this -8 comes from. And now our matrix is in reduced row echelon form. But this form is a little bit different than, say, the matrix that we worked with in the previous video. So let's see how we can make sense out of this matrix in terms of what this tells us about the solutions. So this augmented matrix corresponds to this system of linear equations down here. So I have a 1 for the coefficient of x1, I have a 0 for x2, I have a 7 x3, and that's equal to -8. And this second row gives me a second linear equation. So what I can see from this system is that there's no condition on x3. x3 can be any value that we pick. So we call that a free variable. So I can pick any number that I want for x3. However, once I pick that value for x3, that's going to give me unique values for x2 and x1. So this is an example where this is a consistent system of linear equations. This system has a solution, just the solution is not unique. We have an infinite number of solutions, and that we can see by the fact that x3 is free. And how can we determine that x3 is free? Well, here's the column corresponding to x3, and this column does not have a pivot in it. Okay, so that's how we can identify that x3 is free. The column corresponding to x1, that does have a pivot. The column corresponding to x2, that does have a pivot. However, this column, again, corresponding to x3, does not have any pivot in it. And that implies that x3 is going to be free. And that implies we're going to have an infinite number of solutions. Okay, so let's summarize some of the features of that solution that we found on the previous slide and introduce some new terminology. So we were working with this system of two linear equations. We set up the augmented matrix, And after doing Gaussian elimination, we put it in its equivalent reduced row echelon form. And from this form, we were able to figure out what the solutions look like. And this matrix, this augmented matrix, right, the first three columns correspond to the coefficients for x1, x2, and x3, and this corresponds to constants on the right side of the equation. So for this first column, the x1 column, we have a pivot. And for the second column, the x2 column, we have a pivot. And for the third column, the x3 column, there is no pivot. So the variables x1 and x2, these correspond to pivot columns, and we call these variables basic variables. Whereas variable 3, x3, does not correspond to a pivot column. There's no pivot in this column after we've written in reduced row echelon form, so we call x3 a free variable. So this means we can let x3 be any value that we want, and then we would have to figure out what the corresponding values for x2 and x1 would be to guarantee that when we plug all three values in to these two equations, both equations are satisfied. So whenever we have a free variable, this is going to imply that we have an infinite number of solutions. So we have a consistent system, and this system has an infinite number of families of solutions. And again, the way that we can identify an infinite number of solutions is if one of our variables, the column corresponding to it, does not have a pivot in that column. Okay, so one more video I want to take a look at, which is going to take a look at, well, how can we identify when no solution exists for a system of linear equations?